Hi, welcome to your first calculus video made by Mr. Kintz. Just as a quick reference, the resources are coming from the third edition of the Pearson Calculus book, which we have at Pine Creek High School. Let's get right into it. This is Chapter 2, Limits and Continuity. We're specifically going over 2.1 today, rates of change in limits. We'll talk about average and instantaneous speeds. We'll talk about what limits are, the properties of limits, one-sided and two-sided limits, and then finally kind of a harder subject that we'll talk about multiple times is the sandwich theorem. I'm going to try to keep all of the videos, by the way, under 30 minutes. This one's going to be tight because there's a lot to cover, so let's get going. Average velocity is the displacement of an object over that time interval, which you can see the equation written there. That's one way to write it. Displacement, delta S, displacement position is S a lot of times in physics. So the change in your position over the change in time, using function notation. Plugging in that change in time, you can see the far side of the equation, f of t plus that change in time minus the f of t all over that change in time. And speed, when we're talking about speed is just the absolute value of the velocity. So if the velocity was negative, that usually means it's going down. Speed, we don't care if it's going up or down or what, we just want to know how fast it's going. Okay. Example 1, we're going to talk about an object that's dropped from rest on top of a large lunar building, so we're on the moon, and it falls at y equals, so y is position, equals 5 times time squared, okay, where y is in feet and t is in time, or is in seconds, sorry. What is the average speed of the first 2 seconds? So we know we're talking about average speed, so we really want to know what is the displacement or the delta y over the delta t. So this 5, oops, wrong button. Oh, sorry. I don't know why it's writing that. Hold on one second. Let me erase that. Okay, forget it. Scratch that out. 5 times our second value is the 2 seconds. Average speed in the first 2 seconds. So the second value is 2. We're going from 0 to 2. Squared minus 5 times, it starts at 0, so 0 squared. See, this kind of like, any type of change in y. So this is the change in y from 0 to 2, average speed of the first 2 seconds, over, you can do 2 minus 0, but we know 2 minus 0 is just 2. So I'm just going to write the 2 right there. That equals 2 squared is 4, 5 times 4 is 20, minus 5 times 0 is 0, over 2. We get equals 10. And again, we said this was in feet per second. So feet per second. Okay. Why don't you give this one a try? Go ahead. Hit the pause button if you need to. Okay, so let's see how you did on this. Hopefully you said that delta y over delta t is equal to, let's see, 5 times 3 squared minus 5 times 1 squared because we're going from 1 to 3. Okay, and then you can do 3 minus 1. Doesn't this look a lot like slope? And that's equal to, okay, so 3 cubed is 9 times 5 is 45 minus 1 squared is 1. 5 times 1 is 5. All over 2. 40 divided by 2 is 20 feet per second. Okay, hopefully that's what you got, 20 feet per second. Moving on. Example 2. Find the speed of an object in example 1 at the instant t equals 2. Okay, so before we were finding it over that time from 0 to 2, we used basically the concept of a slope. To find that delta y over delta t sounds a lot like delta y over delta x, which is a slope. To find the speed of an object at an instant, though, we can't just use, we don't really know, we don't have a distance that we're going there. So what a lot of people will say is, well, then why don't we just call, let's not go a distance of 0 at an instant, but let's say we're going to go a distance of a really, really, really small value called h. So we're going to go delta y over delta t still equals, and it's still the same equation, 5 times, okay, we want to go from a little bit more than 2, and that little bit more we're going to say is that distance of h, so 2 plus h. Let's say it was like 0.00001 seconds, then it would be 2.0001, which is that 2 plus h. But we're just going to keep h as the general really small number, okay, and we need to square that, minus, well, if we're going from 2 to 2 point whatever h is, we've got that 2 point whatever h is here. So now I need to do minus the 5 times just the 2 squared. Okay, and then the distance we just traveled, the delta t, is the h value. It's that you could do the 2 plus h minus 2, or just that simplifies just to h. So we're traveling over that distance of h. Like we said, we're trying to find out, this is as h, basically we want to make h as small as possible, so we want to say as h goes to 0. Well, if we were to plug 0 in for h right now, you can't divide by 0, so this isn't going to work. So let's just talk about as h goes to 0, and maybe let's look at it in a little bit of a different way. Let's look at this using the same exact formula, but as you can see, we're going to start with h being 1 second, and then 0.1 seconds, 0.01 seconds, and let's see what happens as we go, so we can make maybe an assumption of what we think the instantaneous speed is going to be at 2. So you can see if you plug it into the table, if you plug it in as 1 second for h, it's 25, so that would be like going from 2 to 3 seconds if you were to do that. The next line is from going from like 2 to 2.1 seconds. The next line is going from 2 to 2.01, and you can see what's happening. The instant, or the average speed during those time intervals, it starts at 25, then it goes to 20.5, 20.05, 20.005, 20.005, and you can see if we got to an infinitely small h, as h goes to 0, basically, we could say that the instantaneous velocity at time equals 2, because if h is at a 0 value, or as it gets really close to 0, that's your instant time at 2. So at time equals 2, the average, or the instantaneous speed, we'll just call it the speed speed equals 20 feet per second. Okay, which is actually kind of interesting. I think that's the same thing you got from 1 second to 3 seconds. That won't always work out that way. That's just a nice little curve there, but that doesn't work for all functions. So don't think you can just go, if we're trying to find the instantaneous speed, you can always go from 1 to 3 and that'll work out that way, because it won't. Now let's see how we would look at this algebraically. Algebraically, again, if we go back to the 5 times 2 plus h squared minus 5 times 2 squared over h. We're trying to simplify this as h goes to 0. Well, let's see if we expand this, if we can get us to not have a denominator of 0 so that it's possible. So let's simplify this. We get 5 times 4 plus 4h plus h squared minus 5 times 4 all over h, and that equals 20 plus 20h plus, that's 20h, plus 5h squared minus 20 all over h. Well, 20 minus 20, those cancel. Okay, so we have 20h plus 5h squared over h. Factor out the h's in the numerator to get h times 20 plus 5h over h. Look at that. Those cancel. 20 plus 5h. And we said we wanted h to approach 0. So as h approaches 0, now if we just plug in a 0 for h, we get this equal to 20. So algebraically, that's how you could simplify the original equation that we set up using h as h approaches 0. Here's another way I want you to see if you can think about this. Go ahead and watch this video here, and you can see using your calculator how you can zoom in on something. Okay, I want you to try now, what is the speed of a rock at 3 seconds? You can use a table, you can do it algebraically, however you want to do it. Go ahead and give that a shot and prove it. If you do it algebraically, prove it with a table. If you do it with a table, prove it algebraically. Go ahead and hit pause on the video. Next, let's talk about what a limit is. So this definition that your book has is, let's just read it. Assume f is defined in the neighborhood of c, and let c and l be real numbers. The function f has a limit L as x approaches c if given any positive number epsilon, that's a little Greek letter epsilon, there is a positive number delta, so that is the lowercase delta, such that for all x, 0 is less than the absolute value of x minus c is less than delta, and that means that the absolute value of f of x minus L is less than epsilon. If that's all true, we write that the limit of f of x as x approaches c equals L, the limit. Oh my goodness, if you got that, then you are way smarter than me. That is confusing. So first off, let's just talk about limit notation. This is how we write limits. Okay, the way that you say it is the limit of f of x as x approaches c equals L, the limit. Okay, this is the delta epsilon definition of these, and the way it's written is really confusing, but let me see if I can make this a little bit simpler by, let me see if I can get rid of that. Undo, undo, undo. No, it's not letting me, unfortunately, so let me just erase it. Okay, back to the pen. Okay, forgive me, first video, first time using this app, so it's going to take me a couple tries to figure this out. But if we have a graph, and our graph looks something like, I don't know, that, okay, and we're specifically trying to estimate the limit of this value here, C, okay, so this is a value of C here, and maybe we know we're trying to find what does that line approach as it hits there. That's L. Okay, the limit as this graph approaches that C value. Okay, so an x value of C, that's that limit as f of x approaches C, or x goes to C, equals L. Okay, if we can estimate this in some distance away, so if we can be accurate to C within some distance here of C plus delta, and then the same distance away over here of C minus delta, that's going to put us in this range here of L plus epsilon and L minus epsilon. So basically all it's saying is if you can estimate D or a delta, if you can estimate C within some error of delta, then you can have an estimate of your limit with some error of epsilon. So we can get as close as we want to be as specific as we want. Like you could see with that calculator when you're zooming in, you can zoom in as many times as you want to get as accurate as you want. With the table, you can keep going as far as you want to zoom in basically as far as you want on your table. But it basically just is saying this. So this is maybe a simpler way of looking at this definition of a limit. It's the delta epsilon definition of a limit. Okay, simple way to think of this is as we're moving along, as our x's approach C, what is this value here of C? What is, in this function f, this is the function f of x, as x approaches C from the left, the way you would write that is as the limit of f of x approaches, or as x goes to C, and the way you'd say from the left is you'd put a little minus sign from the left, because left is minus. Okay, so we're saying as we approach C from this side, what is it equal to? Okay, or you could even say from the right side, as f approaches C from the right side, the way you'd write that is the limit of f of x as x goes to C from the right. So that's all that little plus sign above the C means is from the right. Okay, if those two values are the same, then we know that the limit as x, the limit of f of x as x approaches C is, in this case, we come over here, that y value is L. There. So that's another way you can just think of limits. This is how it's kind of defined. You're just approaching some value, okay, of a function. So we're just zooming in on something like this. That seems kind of obvious, and you're probably going, well, why do I care about this? Or I don't know what you're thinking, but it might be something like that. Well, let's look at an example of where we'd have a hole like this where it's not defined at C, where maybe f of x, it's not possible there because you're dividing by 0 there or something like that. Well, you want to know, as we approach or get close to C, what does it approach from the right and left? Is there a limit that exists there? So let's look at some examples of these situations. Well, just kidding. Let's look at properties first. Properties of limits. So here are 6 properties of limits. They're kind of obvious. The sum rule, if you have the limit of f of x plus g of x as x approaches c, and you know that the limit of x is L and the limit of g is m, then you know that the limit is the limit of f plus g as x approaches c is going to be just L plus m. Difference, you just subtract them. Product rule, you can multiply them. A constant, if you have a constant, you can just multiply that limit by the constant. Makes sense. Quotient rule, if you're dividing them, you can divide them as long as the g function there is not equal, the limit of g is not equal to 0. The power rule, same thing. If you know the limit of f, all right, and it's L, then if you were to be asked what's the limit of f to some power, well, then it's just equal to L, that limit to that same power. Okay, so those properties should be pretty simple. So let's use, if the limit of k, a constant k, as x approaches c equals k, meaning like if you were on some number y equals 2, for example, that's a constant, y equals 2. The limit as x approaches c, well, it doesn't matter. Y equals 2 is just 2. So that's kind of that first part. And the limit of x, so now we just have some function x, as x approaches c equals c. Well, that makes sense. If the equation was y equals x, and you approach some value c, well then it's going to be equal to c. Use the properties of limits to find the following limits. So since it says use the properties, I'm going to use the sum property for the numerator and the quotient property for the denominator for a, and just kind of complicate this way more than it needs to be complicated. But we'll do this first and then it'll become simple here in a second. So if we said that the first part, f of x is equal to y squared, and g of x equals 5y, h of x equals 6, hi of x equals y, and j of x equals 2. So I'm basically just splitting that whole thing into a bunch of different functions so that we can find each of these limits. Then we can say that, okay, the limit of y squared as y approaches 2, well, substitute in a 2 there, you get 2 squared equals 4. For the next part, g of x, if we said the limit of g of x, which is 5y as y approaches 2, is equal to 5 times 2, which is 10. Okay, and you did that for all of them. Well, 6 is a constant, so if you were doing the limit of h, that would be the limit of 6 as x goes to 6, which is just 6. That's kind of the first part up here. The denominator would be just 2 plus 2. Basically, it would simplify to, I know we're trying to work on these properties so you can see that they work, but it's really overcomplicating this. Just, if it's asking you, when we're dealing with limits, if it's asking you to go finding a limit to a specific value, just try to use substitution first. If it doesn't work, we can complicate things a little bit. If it does work, awesome, we're done. So let's do that instead of wasting all this time. Sorry, I'm trying to keep this under 30. I don't think we're going to make it. So we do 2 squared plus 5 times 2 plus 6 all over 2 plus 2. So we substitute this in. We want to make sure that this is possible. Are we hitting some value? Are we breaking any rules? I don't see any 0 in the denominator, which is what we run into the most. So we can just do this. That's 4 like we said before, plus 10 like we said before, plus 6 over 2 plus 2. If you wanted to use the quotient rule, if you made two new functions, like the numerator was a function, the denominator is the function, and you wanted to divide them, you could do that using properties. Anyway, 20 divided by 4 equals 5. So we could say that the limit of this whole thing is equal to 5. So very, very simply, I want you to do what I did on the second part, just substitute in. So it's going to be super easy. Do part B for this next part here. Okay, so hopefully you said that this is the limit as x goes to 2 of the square root of x plus 2. Shoot, I hope it was 2. Nope, it was 3. Let me erase that. Oh, it's not letting me erase it. Okay, so we're going to just write a 3 over there. Okay, is equal to, well, you can just plug that in. Square root of 2 plus 3, which equals the square root of 5. So the limit the limit of the square root of x plus 3 as x approaches 2, make sure I say it right for you, is equal to the square root of 5. Okie dokie, moving on. So this is what simplifies that. So if you look at this one, if it's a polynomial, if f is a polynomial, then all you do is substitute in. So that's basically what this says. If f and g are polynomials and c is any real number, again, substitute in. If you're going as x approaches c, substitute in whatever that value of c is there. That's what we just did, instead of kind of going slowly through all those properties. Okay, so this would be one where we are trying to find the limit of something, of a specific value. We're going as x goes to 0 here, so if we try to substitute this in, we get sine of 0 over 0. We can't divide by 0. So since we can't divide by 0, we can't use this here. So we can always go back to a graph. We can look at a graph and you can see as it's graphed here as f, or as the limit of the sine of x over x as x approaches 0 from the left. Okay, so as we're approaching this value here from the left, all right, well, that looks like it hits that value. If you couldn't see before, it looks like on here that's a value of 1. So we'd say that is equal to about 1, just looking at a graph. Okay, if we're going from the right side, what does it look like it's going? We'd write it out as what is the limit of the sine of x over x as x approaches 0 from the right. That also looks like it is about at 1. Okay, if you look at a table, you can see from the left as we go this way, it looks like those numbers are approaching 1, 9.850 to 0.98507, 0.99335, 0.99833. At 0, it's an error. Again, you can't divide by 0. So just because this function doesn't exist at 0 doesn't mean that its limit does not exist. it means this is not a continuous function. Okay, you'd have to pick up your pencil while you're drawing this technically. Draw a little dot there. This is a picture of a graphing calculator. It doesn't put a dot there, so it looks like it's continuous, but it's not because of the 0. So you can see there, we get the same thing. From the left, it looks like we're approaching 0. From the right, or sorry, approaching 1. From the right, we're approaching 1. Because of those two things, we can say that the limit of sine of x over x as x goes to 0. Because the limit of the left looks like it equals 1 and the limit of the right looks like it equals 1, then we know that the limit as x approaches 0 is equal to about 1. Okay. So I try usually not to use examples that your book uses, but I wanted to use a product rule specifically so you can see how we can take some of these, knowing what we already know since we just used and saw what the limit of the sine of x over x as x approaches 0 equals 1. I wanted to use one that used that same concept. So right now we can't do anything with this except for maybe rewrite this into two different functions. So if we were to rewrite this and say that this is the same as the limit of sine of x over x times 1 over cosine of x. Okay, and we can rewrite it like this because we know that tangent is sine over cosine, so we just kind of split that up a little bit. So if I rewrite it into these two functions, okay, I know that the sine of x over x, we just found out as, oh I forgot to say, as x approaches 0, we know that the first part of this, that sine of x over x is going to be 1. So we know that that first limit is 1. So what we really need to find, since we know the limit as x approaches 0 of the sine of x over x is equal to 1, what we need to find is the limit as x approaches 0 of 1 over cosine of x. Well, remember, when we're approaching a value with limits, we want to try to use substitution first. So just plug it in. What is 1 over cosine of 0? Well, cosine of 0 is 1, so we know that this is equal to 1. Well, using the product rule, if you know the limits of two different functions, then you know that this would just be 1 times 1, which equals 1. So we can say that the limit of tangent of x over x as x approaches 0 is equal to 1. That's using the product rule. Okay, I've been talking about this already. This basically just shows a function f has a limit as x approaches c if and only if the right hand and left hand limits at c exist and are equal. So there you can see it's written down there. So they exist and they're equal. It makes sense if the limit from the left equals the limit from the right, and those are, and they exist, I guess that's important to add in there, then the limit exists. Okay, well let's look at one that possibly the limits do not exist. So here we go. Do this with G. I want you to try this. Part A says, using the graph below, what is the limit of G as x approaches 2 from the left? That's what A says. So go ahead and give that a try. Hit pause if you need to. Okay, hopefully you said that as G approaches 2 from the left, we're talking about as G comes down here, where does it approach? G approaches, well, this y-axis isn't labeled, so we just assume that this is a 1. So it looks like it approaches a value of 1. So hopefully you said this is equal to 1. Okay, part B says, what is the limit of g of x as x approaches 2 from the right? So we're talking about that. So go ahead and hit the pause button. What do you think that is? Okay, hopefully you said that also is equal to the 1 from the right and the left. So using the last rule, if the limit from the left equals the limit from the right, which these two do, and they exist, one exists, I'm pretty sure, then we know that the limit of g as x approaches 2 is equal to 1. Okay, part D says, what is g of 2? Well, be careful here. G of 2 is defined up above. This is not a continuous function. We had to pick our pencil up. We had to draw at g of 2. G of 2 is actually up here at 3. So g of 2 is 3. Okay, so this is not a continuous function, but the limit of g is 1. So the limit of g you can see here is different than the actual value of g. This is why it's important to discuss limits. A limit of a function versus what a function is actually equal to. Okay, now I want you to try this. What is the limit of g as x approaches 0? So find the limit from the left and the limit from the right. If those two are the same thing, then what is g? Hit pause. Okay, hopefully you said that, well, it looks like the limit from the left is approaching, well, this is just going to go up forever, even though there's not an arrow, it disappears on this graph. So it goes up to, infinity. From the right, it's going up to infinity. Well, infinity equals infinity, so g must equal, as x approaches 0, infinity. That would be fine. Say positive infinity. A lot of people will put a plus in front of that because it's different than negative infinity. So maybe be more specific and say positive infinity. Okay, but a lot of people will say, well, infinity doesn't exist. So this would be that time where you'd say, well, the limit from the left does not exist because it approaches infinity. The limit from the right does not exist. Or we can basically stop there and just say, since the limit from the left does not exist, this does not exist. So either is right. You could say this is equal to positive infinity, or you can say that this does not exist, because I guess technically infinity doesn't exist, even though it does exist. I don't know, my mind just exploded, I think. Alright, this is the hard part. Sorry, I think we're already at a half an hour and we've just gotten to the hard theorem. If some function g is always less than or equal to the function f, which is always less than or equal to the function h, and it's called the sandwich theorem because f squeezes in between g and h. It can be equal to one or the other, but it's never smaller than g and it's never bigger than h. For all x not equal to c in some interval about c, okay, and the limit of g of x as x approaches c equals the limit of h as x approaches c, which is some limit L. Okay, that would mean that f, since f is between the two, the f has to also equal L. Okay, it's that sandwich theorem. If we can find the limit of function g and the limit of function h, and they're the same thing, all right, then we know f has to also be the same because f is in between them, so if they're equal, they have to be equal. Okay. Let's look at this one then. Let's break this up a little bit and just start with, we know that the cosine of 2 over x is always between -1 and 1. So we can kind of start there. We've got this function is always going to be less than or equal to. Cosine can be equal to -1, all right? But it's -1 is always less than or equal to this cosine, and cosine is always less than that 1. So it's, like we said, cosine is between -1 and 1. We've just made a little sandwich here with two outer functions. Okay, but let's get to what we're looking at here. Let's say, not just that, let's multiply everything here by x cubed. So let's change it to -x cubed is less than or equal to x cubed cosine of 2 over x less than or equal to x cubed. We did change the look of this, but we changed them all the same. We changed them all by multiplying them by x cubed, so it's a legal move. If you're using substitution, elimination, that kind of stuff, you remember you can do this as long as you do the same thing to each function or each side of an equation or whatever you're doing. Okay, so this was legal. We just changed it here. Okay, and we can say now, I know that the limit of negative x cubed as x approaches, and this is getting very specific, 0 from the left. So as we come from, like let's say -3, -2, -1, all the way as we approach 0 for negative x cubed, well, you can just substitute that in, you get 0. I also know that the limit of positive x cubed as x approaches 0 from the left is equal to 0 as well. I just substitute that in. Since those two are equal, since those two limits are equal, and we know that x cubed cosine of 2 over x is between those two, we've just sandwiched it. It also, so the limit of cosine of 2 over x as x approaches 0 from the left, it also has to be equal. Oh, I'm sorry, I forgot the x cubed here in front. The limit of x cubed times the cosine of 2 over x as x approaches 0 from the left also has to be equal to 0. That is the sandwich theorem. It's kind of confusing, but it would have been really hard for us to figure this out without using a calculator or a table of what the limit is. So if we just had to go algebraically, the sandwich theorem helps us solve these limits algebraically that we wouldn't normally be able to probably figure out. Okay? I hope this helps. I hope this was a good first lesson for you. Bring in any questions that you have. If you weren't able to figure out something, or if I made a mistake somewhere, please bring those in so that I can go back and edit these videos and make them better for next year. So thank you very much, and I hope you had your first good homework assignment video. Thanks.